This is my video demonstration for the Independent Innovator final product, where I made a basic evolutionary simulation. The general setting is of the bottom of a lake, where we have different microbes, which can either be protozoa or bacteria, which I'll talk more about. So on this website, which I'll have a link for you to be able to try out on your own if you'd like, just has this canvas here which contains the view of the simulation. So this setting is the lake bottom, and then here we have these what appear to be green cells right now are the protozoa, and then these gray blocks are the bacteria. And down here I have just a basic user interface for making customizations so that you can intervene into the simulation and see the results of your intervention. So first, this is generally supposed to model the interactions between predators and prey, where the protozoa are the predators and where the bacteria are the prey. So as you can see, the protozoa, the green, are moving around quite a lot because they actually are considered like the more complex organisms here. They have their own energy and movement and reproduction, and they're the ones that are actually evolving, while the bacteria just stay still and get consumed. So it kind of might look like they're moving, the bacteria is moving around. That's only because for any given block, it spawns at a constant rate. So see here, there's a setting for bacteria spawn per step, and right now this pattern is set to random, so the bacteria just spawn in a random place in the lake. That's why they appear, and then whenever a protozoa comes across that cell, then that bacteria is consumed by that protozoan, and then the bacterium disappears. But the bacteria themselves don't actually move around. So if I press kill all protozoa, then you can see the bacteria keep spawning until they hit 6,000, which was set as the max number over here, and then they stop moving because they don't move. In real life, bacteria do move, and they also can evolve, but in this context, it was easier to just model them as an energy source. But if you were like a professional biologist doing actual research, then you would try to make the simulation more complex and more realistic, so that it gives you better information about these kinds of patterns. So first I'll kind of explain what the protozoa are made up of and what they represent. So each protozoan has a genome which represents that protozoan's genetics, and a genome is just here 8 numbers from 0 to 7, where each number essentially represents the probability of making a certain change in direction. So an easy way to see this is through these two parts of the configuration. Average genome shows the average value for each gene across every alive protozoan. So if we had like one protozoan with a value of 0.5 for gene 0, and then another one with the value of 1 for gene 0, then the average here would show 0.75. But right now it says -1 for all of them because there are no living protozoa. So if we spawn them in, like by clicking here, and you can see it becomes greater than -1 and it starts shifting around. The reason it's changing is because some protozoa are dying, so they get removed from the pool of averages, and some are reproducing, so their offspring are added to the pool. And you can see that there's kind of like a trend towards increasing gene 0, which I'll explain later. So I said that each gene was a representation of the probability of making a certain change in direction. So I can demonstrate that more thoroughly here. I'll just kill all of them and then remove the bacteria by setting the number of bacteria spawned to 0 and then pressing kill all bacteria. So down here, in this hardcode user genome section, we can set our own custom genome and then spawn protozoa that have that genome. So first I'll just set a basic of gene 0 is 1 and all the rest of the genes are 0. So since these represent probability, and it's a probability from 0 to 1, that means basically that there's a 100% chance that the genome will make a 0 change in direction, and then a 0% chance that it'll make any other change in direction. And I can basically draw out how these changes in direction are supposed to look like. Do I have like a fill? Sorry, it's kind of laggy. Okay, so each protozoa always has a direction that they're pointing in. So let's say this is my protozoan and they're facing in this direction. Now each of these directions is relative to the direction that they're in by default. So since they're pointing up, that's where I'll start, and that's what 0 represents. So if the protozoan does a 0 change in direction, that means that they point in the same direction that they were already pointing in. Then 1 is to the right of the 0, and 7 is to the left. And then it goes 2, 3, 4, 5, and 6 like this. So if the protozoan made like a 3 change in direction, that means compared to whatever direction they were already in, they'd make like a hard right turn. And if they had like a 7, that means they'd be doing a slight left turn. So for example, if we had another protozoan over here pointing in this direction, then if they made a 7, they would now be looking in this direction. It wouldn't be this one. So each of these genes represents the probability that they will be making that change in direction. So since it's a 100% probability for a 0, that means that every protozoa with this combination of genome will always move forward infinitely and never switch direction. So if I just spawn one of them, oh, okay. So see that one still moved around and switched direction a lot. That's because I didn't have this set to active. So then it just uses a random genome. If we activate this, there. Okay, I'll just, so see, it's moving like this, and it's popping up at a different point of the screen. That's because this is kind of, it's drawn as a rectangle, but it's basically like a sphere that loops around. So here, can we get like a better, yeah. So it goes this way, and then it hits this edge and loops around to the other way here. Where do I have, yeah. So when it was going diagonally, it moved down here, and then it went off this edge, so it wrapped around to here, and then kept going in the same direction. Then when it's like here, it wraps around to here, and so on. So see, it comes out there, this will come out like here. Okay, I can't really track the position very well, but you see the idea. So if we had like only 1 for 1. So remember, this is a slight change in direction to the right. We see it just goes in a circle infinitely like this, because it just always goes right. So if we have like a 0.1 here and then a 0.9 here, this would mean that there's a 90% chance of going in direction 0 and a 10% chance of direction 1, so going slightly to the right, which means we'll see like more of a spiral pattern. Yeah, see, it's like mostly going forward and then occasionally switching, right? So this basically is entirely what determines the the protozoa's behavior. So they can't actually react to the environment, they just have a genome that specifies how they should behave. And then they basically have to get lucky that their genetic specified movement that corresponds with where the bacteria are, so they can consume the bacteria and gain energy. And how evolution happens is that the more successful protozoa, who happen to have better genetics that let them have more food, will have more offspring, and they do asexual reproduction, so they just basically clone themselves, and they have some chances at mutations of their genes, and eventually over time we'll see evolution, because they'll have those random mutations, and the more successful mutations will be passed down to future generations. So then I can kind of reload again. You can see over here, so a lot of them die at the start because their genomes are completely random, and a lot of genomes are very just not performant, because protozoa lose 1 energy per step just for living, but they also lose energy based on the severity of their turn. So if you make a slight turn to the left or right, you'd lose a little bit of energy. If you make a hard turn, then you lose a lot more energy. So if a protozoan is just like moving a lot in a circle, then not only will they not get that much bacteria because they're not spreading out, they're only staying in the same spot, but they're also losing a lot of energy that they're wasting changing direction. That's why we see a trend towards having a higher value for 0, which is where they just go forward so they can get more area, and they can avoid losing energy for switching direction. But you still have to like move it a little bit, because I can show, like, if we just told the protozoa to move only in 0, so never change direction, then, well, this one was more fortunate. But see, it's just moving in the same lines, and those lines will kind of loop around, and yeah, it died. So the bacteria spawn randomly, and this protozoan who goes only in a straight line only covers the same space over and over. So it's easier to see if it's going, hold on, it's easier to see if they're going up or down. Yeah, so here, if this protozoan is just going like this, then the only area they ever cover is this one line. In this case, that line was enough for them to reproduce, get an offspring, and then for that offspring to mutate into having a different gene for changing direction. So that's why their offspring was able to change direction, and they are now flourishing pretty well. But if it was only, or here I can set like the gene mutation rate to 0, and then just going straight again. It's easier to see when they're going in vertically or horizontally. Yeah. So now see, this is like already empty and no more bacteria are going to spawn here because we're at max bacteria. So this one is just going to die. Yeah. That's why it's important to have at least a little bit of change in direction. So here basically the protozoa die when their energy hits 0. They have a certain number of energy that they spawn with. Then they lose energy every step. And a step is just like one new iteration of the simulation. Like if we press stop here, spawn one, then we can go on individual steps. See, so like each of these, they're losing one energy, and so after 750 they would just die. But if they were like turning, then they might die faster because they'd be losing more energy. But that would also make it more likely that they get some bacteria, which right now we have set to 40, which means each time they get a bacteria they gain 40 energy. And once they reach this threshold for reproduction, which is set to 1000, then a new offspring will be created. There'll be some chance of mutating based on these settings, and then half of the energy of the parent will be sent to the child. And so that child can now go around and have its own offspring. Yeah, that's the main idea. And then there's just all these settings I made for trying more different configurations. So here we have these. Oh yeah, and the color of the protozoan basically just represents, yeah, I said that the genome. So the green ones all mostly represent ones with higher 0 values, and then you'll have like some pink and blue ones which have lower 0 values and higher like 4 values. You see there's like some variations in color, but they will mostly trend towards green because that's generally more successful. In here, if you like, you can hard code something. Generally the most successful one, in my opinion, but I haven't like seen every possible combination, is something like this, where in most cases you just go forward, but occasionally you go left and right. So you can see these do pretty well. And they're just limited by the total number of bacteria, because the higher the population is, the more they eat, and then the less bacteria that each of them can have for themselves. But you can see, like, if we remove the bacteria, these will be reducing. You can see that they mostly go straight, but then occasionally make changes. Here you can also, I guess I'll just like talk about some of these settings. So pixel scale, it basically just represents how large this screen is. If we do like 6, that means we'll have 6 pixels for each cell in this grid. It looks like in this starting point, this orange population is doing better, which has like a higher value for 2. But they will probably still trend towards green. Here, width and height just show like the width and height of this of the lake. Duration of one step is just like in milliseconds how long each step takes. So if we do like 1000, that's 1 second per step. Like that might make it easier to see some things. This is what change in the protozoa's energy happens per step. So right now, -1 means they lose 1. Here, this is like a multiplier on how severe the energy loss is for movement. So if we make this for a change in direction, so if we do like -10, then they pretty much all die instantly because they're still moving around. But if we had like a lower value here, like maybe you gain energy for staying still or just for existing, then it could be optimal to just have a high value for 0 and just do no movement, because then you wouldn't even need any bacteria. You could just survive by never changing direction. We have a limit on the number of alive protozoa. This is mostly just so that it doesn't lag too much, because your browser can't handle an infinite number. There's an energy cap, requirement to reproduce, how much they change from getting a bacterium. So you could also make this negative if you wanted them to lose energy from bacteria, and then they'd have to kind of evolve to avoid the bacteria. Here, this is the rate at which genes mutate. So that's like every time they reproduce, each gene runs this probability. So 0.125 is 1 in 8, which means each of these will have a 1 in 8 chance of getting a mutation. And then this is just like how large the range is in new values. So 0.125 can be added or subtracted with something in between to whatever gene is being mutated. Then there's the number of bacteria spawning, the max number of alive bacteria, and then finally there's this pattern for where they spawn. Right now the bacteria are just spawning anywhere, but we can say like this circle option. So you see they just spawn in a circle in the center, and now the protozoa will have to evolve to make a lot more movement, change in direction, because if they just move forward with 0 all the time, then they'll go out of range of this circle, and like these over here, and then they'll just die from starvation because there are way less bacteria over here. There's just the ones that existed before we switched it. So we kill it like this, then now all of them pretty much die out here. So they're like going to be shifting to having higher probabilities for other changes in movement. And here we can like also choose where to spawn the protozoa. So if we say like center, these spawn in the center. Random is anywhere on the screen, so here most of them will die. And then lines, these spawn like, you can see in horizontal, vertical, and diagonal lines, which also corresponds with this third option, lines. You see now this is more difficult. A large portions of the space in between here has 0 food. So if they're just walking around in like mostly straight lines, then they might get trapped over here. Here it's a pretty good strategy to stay in the center still, because you have food all around you in different directions, even if there are some pockets here. But here the eventual best strategy would be to usually stay just in the same in the same direction without switching manually, and just going across these lines up here. So if we set that manually like this and just spawn them in the center, you see there's a bunch now that are just going to move across here, and they'll always be getting all of the new bacteria that are spawning across there, unlike these over here. There are also some that were we spawn them like in the center, there's some that go diagonally, but their direction is like 45 degrees, which doesn't match this. This is like from here to here, it's like this angle is less than 45 because the width is greater than the height. So if we set like the width to 100, killed all the past bacteria, we can kill these two and then just like spawn them in the center, and see now they're way more successful because they can go right along these tracks that have all these bacteria over here. You can also like spawn them on the lines, then they do really well. And here we can also correspond them with random genetics, or we can get rid of the bacteria first. And then maybe switch this to like 40, so it's more filled in. We'll do like 80. Yeah, but still, like most of them don't know how to consistently move around in a way that can keep up with the line. They eventually like get off track and then die out here in the empty space. So that's why there's still much more of them in the center where they can more easily get back on track. Yeah, I guess that's about it. This took a little longer to make than I thought. Here I have the code. I have 714 lines in here, but this includes like the comments and the empty spaces. I have like all these configuration options which map onto here. This HTML describes like the structure of the page. And then I just have code that has to watch for changes and then update the internal JavaScript to match it. And then the actual code for like deciding how to change their direction based on the genome, how to like mutate their genes. There I had to come up with a way to like spread out changes. So if this gene 0, like let's say our only genes were like 0.5, 0.25, and 0.25, and now we decided to like add 0.25 to this one, let's say like 0.3, then this one will become 0.8, but these have to be subtracted because we still need the entire thing to add to 100%. It can't be like this one is 80% and then these are 25 and 25. That wouldn't make any sense. Then we have to decide how to subtract these collectively by 0.3. So I had to come up with an algorithm for that and debug it when some things went wrong. But overall I think it works pretty well. Yeah, alright, I guess that's about it. Oh yeah, this is just like, and you can determine how many to spawn. So if you do like 3,000, it lags more, but there's a bunch.